Hello everyone. Today we shall discuss about work, energy and power. You see, work can be defined as in this way that work equal to F dot D. Displacement is a vector and F is a force. But even then work is a scalar quantity. Remember that work is a scalar quantity. Work is a scalar quantity. Scalar quantity. The reason is that why work is a scalar quantity, because it is a dot product or scalar product of force and displacement. And kinetic energy is half mv square. Work, energy and power. A notebook on the mechanics of motion. And P is momentum, right? Or P can be written as power, right? Here it is not momentum but it is power. Power is equal to F dot V, that we are going to discuss. Energy is the currency of the universe. Work is how we spend it. Right? Now we are going to next thing, that is this one, that is the mathematical toolkit scalar product. I already told you. The scalar product of two vectors A and B is a quantity defined as vector A dot vector B is equal to modulus of vector A modulus of vector B into cos theta. Right? Where theta is the angle between them. Key properties. It has commutative properties that A dot B vector is always equal to B dot A vector. Not only that, distributive A dot B cross B plus C vector equal to A dot B vector plus A dot C vector. Unit vectors I dot I is 1, I dot J equal to 0, right? According to these properties of A dot B. In this way you can define the scalar product. So scalar product, if the scalar or dot product of two vectors is always a scalar quantity, just as work. I already told you that work is a scalar quantity as it is the dot product of force and displacement. So we got it as modulus of F into modulus of D into cos theta, and theta is the angle between F and D, and theta is the angle between force and displacement, between force and displacement, force and displacement. This is the definition of work. Now we'll go to the next slide and you see here what is given. Defining work, the physical interaction. I told you work is equal to F dot D. It is F is a vector and displacement is also vector, is F D cos theta. You see here, if this is D, if it is F, this F can be resolved in this direction, that is F cos theta, and if we multiply the F cos theta with D, that is as work done. In the same way, the zero work paradoxes, displacement 0, work equal to 0, theta equal to 90 degree, and cos 90 is 0, the work equal to 0. A person taking a suitcase, he moves in this direction, the displacement in this direction, the force in upward direction, therefore the theta is cos 90, therefore it is 0. There are three cases in which the work done is 0. Why? Because you know that work done is equal to, we know this is that F dot cos theta or modulus of F into modulus of D into cos theta. There are three cases arises in which the work done is 0. Well, number 1, if force is 0, then work done will be also 0. Number 2, if displacement, that is D is equal to 0, then it is also work done is equal to 0. And third point is that if theta, the angle between force and displacement, is 90 degree, then the work done will also be 0. For example, this is our sun and this is our earth. The attraction between earth and sun is always towards the sun. that is, it is inside the inside of a circle, and the displacement of this earth is always perpendicular to the radius. So the angle between force and this is the force, and displacement is in this direction d. If the angle between them is always 90 degree. So the work done in revolving earth to the sun is always 0. In this case, the work done is also 0. So we have to remember all these things, right? So we have to remember all these things. Next point is, you see here, that is kinetic energy and the work energy theorem. Derivations flow. Newton's equation, you know that v square minus c square equal to 2a into d multiplied by m by 2, 1 by 2 mv square minus 1 by 2 m square equal to m into a into d, right? And since F equal to ma, therefore del change in kinetic energy equal to F into d, force in displacement, the change in kinetic energy is equal to force F dot d, that is work done, right? So work done equal to change in kinetic energy. Therefore, theorem, work done by net force equal to change in kinetic energy. The raindrop case is steady, mass Ig, distance 1 kilometer, work gravity work 10 joule, work resistance minus 8.75 joule, network 1.25 joule, final kinetic energy. Here resistance negative work, gravity positive work. So in this case we can find the raindrop case study. Now we find the next important thing is that of work done by a variable force. Here you can show this is the position, this is the force, right? We will find the work under the curve to find the work done by variable force. So work done can be find out by Fx into dx, right? This is the work done. Area under the curve, that is the work done, right? So this is the force in Newton, and this is the position of the mass in this direction, right? So area 1 rectangle, this rectangle, right? Rectangle. Area 2 trapezium, this is a trapezium. So the total work is 1750 joule. You see rectangle 100 into 10. You see this is 100 and this is 10. Length into breadth 100 and 10. This rectangle. And this is a trapezium. What is the formula for trapezium? Half into a plus b into h. Half 1 by 2. A is how much? M is, this is 100 and this is 50 by 2 into 10. This is 10. So this is 750 joule, 1000 joule, and total work is 1750 joule. So work done by variable force is always work area under the curve, that is given by W is equal to integration of Fx dx. This is the formula for work done by a variable force. So to find the variable force, you have to find the work done or work under the curve. Potential energy is the stored capacity. Energy by virtue of position or configuration is stored work waiting to be released. Gravitational potential energy V is equal to mgh, and force relationship minus dv by dh, and that is equal to dv by dh is equal to minus mg. You can see here dv by dh is equal to minus mg. Compressed springs of the earth, gravity ready to act, it is external work is stored. It is stored as a potential energy. Here it is stored as a potential energy, right? Compressed springs of the earth. Potential energy is defined only for conservative forces like gravity, never for friction. Remember that potential energy is defined only for conservative forces. What is the conservative forces? Conservative forces has three characteristics. Number one, that conservative forces depend only on initial and final position, right? That is conservative force, conservative force depends only, conservative force depends only on initial and final position, initial and final position, and final, initial and final position. Conservative force depends only on initial and final position. Number two is the work in a closed path is equal to 0. That is the definition in conservative force. This is the characteristics of conservative force. Conservative force depends on the initial and final position, and work done in the closed path is equal to 0, and it is independent of path. Number third, what I told you, it is a conservative force is independent of path. Conservative force is independent of path, is independent of path. These are the important characteristics of conservative force. The next one is what you got here is elastic potential energy, the spring. Hooke's law. It is defined by Hooke's law, F equal to minus kx, and potential energy Fick's law half kx square for a spring. This is a relaxed position, the equilibrium position. This is stretched and this is compressed. Right? In all these cases, see energy versus displacement. This is the total mechanical energy. This is the kinetic energy. You can see here, this is the kinetic energy. The kinetic energy maximum at equilibrium, right, and minimum at the extreme point. And this is the potential energy. See, the potential energy is maximum at the end. The potential energy, right? The potential energy is maximum, that is half kx square or 0.5 kx square, and this is the total mechanical energy. You see here, the potential energy is maximum at the extreme point. The potential, and at the equilibrium position it is 0. So the total mechanical energy is this straight line, that is this is kinetic energy plus potential energy. So this is the elastic potential energy of a spring. Now you find here the next important thing, conservation of mechanical energy. The total kinetic energy is equal to kinetic energy plus potential energy equal to constant, varied only for, remember this is valid only for conservative forces. And I already told you the conservative forces, that conservative forces depends only on initial and final position. It is independent of path, and the work done in the closed path is 0. These three characteristics of conservative forces. And you see point A is here, minimum potential and maximum kinetic energy. At the point C, maximum potential and minimum kinetic energy is 0. So half m v square equal to mgh. You can find this relation. Half m v square equal to mgh. That means that potential energy is changed into kinetic energy at the point A. Right? You see the different points here also. Non-conservative forces or friction. When energy is lost to heat, del D equal to work NC, non-conservative. The car crash simulation, ideal, no friction. Here you see, no friction, x equal to 2.00 meter. And real friction, that is friction, the friction is there, so it is 1.35 meter. Energy lost to road and heat. So this is non-conservative forces. Friction is a non-conservative force. And changing kinetic energy, changing energy is equal to work, non-conservative. These are the two examples we have given for non-conservative forces. This one is power, the rate of work. It is not just about doing the work, it is about how fast you do it. Average power equal to work done by time taken. Instantaneous power equal to P equal to F dot V. How this F dot V came, that if we want to know, that can be here done in this way. Work done is what? Work done is F dot D, right? F dot D divided by time. And you see displacement by time, that is velocity. So power, instantaneous power is force dot velocity. And dot product means power is a scalar quantity. So power is a scalar quantity. Units 1 watt equal 1 joule per second, 1 horsepower equal 746 watt. The elevator problem, this is our load is 1800 kg. There is gravity, there is a friction for 4000 Newton, gravity is mg, and motor tension and the velocity is 2 meter per second. Total force needed, that is 18,000. Total force needed is 18,000 Newton, 18,000 Newton plus 4,000, 22,000 Newton Power is equal to 22,000 Newton into 2 meter per second, 44,000 watt, or power equal to 59 horsepower. So in this way you can find the rate of work. Next point is this one, that is collisions, impulse and chaos, the golden rule. Total momentum is always conserved. The initial momentum is equal to final momentum. Elastic collision, momentum conserved, kinetic energy is also conserved. But in case of inelastic collision, momentum conserved, kinetic energy lost to heat and deformation. Perfectly inelastic, momentum conserved, objects stick together. This is perfectly inelastic. There are three types of collision. Elastic, momentum is conserved and kinetic energy is also conserved. Inelastic, momentum conserved but kinetic energy is not conserved. In the case of perfectly inelastic collision, momentum conserved, objects stick together. This is perfectly inelastic collision. Number 3 is elastic collisions, one dimension special cases. Case 1, case 2. Equal mass. If the mass is equal, this m and m is equal, m equal to v equal to 0 here, so m v equal to 0 here and m equal to v. Now this is velocity exchange. This mass will have velocity and this m will be 0 if the masses are equal. In case to the massive target, suppose this is a big mass, mass is much greater than small m, it will strikes, this m will return back and this mass of this m will be 0. This is the reflection. So in this way the work is done. Application: nuclear reactors use light nuclei moderators to slow down neutrons via gas, right? So these are the very important things you can find it in types of collision. Collisions in two dimensions. Glancing collision, the billiards rule. You see, this is a glancing collision you have shown here, that is V1I, this is M1, right? And this is what is V2F, this is M2, and this is theta 1, right? That is M1, V1F, that is V1F. In this way, right? This is actually M2, right? And so what you get here, that is if the masses are equal, M1 equal to M2 and collision elastic kinetic is conserved, so theta 1 plus theta 2 is equal to 90 degree. So theta plus theta 2 is equal to 90 degree. In this case, we can, this is the billiards rule. We can define this in detail for another video. And the next important thing is a field notes summary. What is work energy theory? That is total work is equal to total kinetic energy varied for all forces, right? So conservation of energy, that is total kinetic plus potential equal to change in kinetic energy plus potential energy equal to 0, the conservation of energy, that is no change in kinetic energy plus. So valid for conservative forces. This is valid only for conservative forces. Conservation of momentum, total P, change in momentum is equal to 0, valid for all isolated collisions. Equivalencies, work, area under fx graph, power, slope of work time graph, and force minus slope of vx graph. So all these are needed for this field note summary. Thank you everybody for watching this video.